The probabilistic model is now complete, a sample space of possible outcomes and a probability law that gives each event its likelihood. But probability is rarely frozen. The moment we learn something, a partial clue about how the experiment turned out, the odds should shift. This chapter is about exactly that: conditional probability, the mathematics of updating beliefs in the light of information. Across 4 videos, we will define conditioning, assemble probabilities across a partition with the total probability theorem, invert them with Bayes' rule, and finally ask when information changes nothing at all, independence. We begin at the foundation, conditioning on an event. Start with a fair die, 6 faces, each with probability 1/6. Now someone tells you the face is odd. 3 outcomes survive, 1, 3, and 5. The even faces are gone. Before the clue, those 3 were equally likely, and nothing about the clue breaks that symmetry, so each now carries probability 1/3. Notice what happened. We discarded the impossible outcomes and renormalized the rest so they sum to 1 again. So the probability of rolling a 3, given that the face is odd, is 1/3, which we can write as the probability of 3 and odd divided by the probability of odd. Here is a second way to see the same formula. Imagine repeating the experiment a huge number of times, n. Count the trials where B happens, and among those, the ones where A happens too. The fraction of B trials that are also A trials is the conditional probability, NAB over NB. Divide top and bottom by n, and each count turns into a probability, so this ratio tends to the probability of A and B over the probability of B. That limit is the definition. For any event B with positive probability, the conditional probability of A given B is the probability of A and B divided by the probability of B. It rescales the law so that B becomes the new certain event. Is this new object really a probability law? It is. It obeys the same 3 axioms. First, non-negativity. A ratio of 2 non-negative numbers can't be negative. Second, normalization. Condition the whole sample space on B. The probability of omega in B is just the probability of B, so PR of omega given B is PR of B over PR of B, exactly 1. Under the conditional law, B carries all the probability. And third, additivity. If events are disjoint, intersecting each with B keeps them disjoint, so their conditional probabilities add. All 3 axioms hold. Conditioning yields a bona fide probability law, and every rule we proved last chapter still works inside B. Let's use it. A fair coin is tossed until the first heads. The probability that this takes exactly k tosses is 2 to the minus k. We showed earlier that the number of tosses is even with probability 1/3. What is the probability it took exactly 2 tosses given that it was even? That's the probability of 2, 1/4, over the probability of even, 1/3, which is 3/4. Knowing the count was even makes 2 quite likely. Conditioning also runs the other way. It lets us build up the probability of several events all happening together. Rearrange the definition. The probability of A and B is the probability of A times the probability of B given A. Now iterate. The probability that a whole list of events, A1 through AN, all occur is the probability of the first times the probability of the second given the first times the third given the first 2, and so on down the chain. This is the chain rule, and it falls out because the conditional probabilities telescope, each denominator cancels the previous numerator. It is tailor-made for drawing without replacement. An urn holds 8 green balls and 4 gray ones, 12 in all. We draw 3 and ask, what is the probability all 3 are green? The first draw is green with probability 8 over 12. Given that 11 balls remain 7 green, so the second is green with probability 7 over 11. With 2 greens gone, 6 of the 10 left are green, 6 over 10. Multiply along the chain. 8/12 times 7/11 times 6/10 is 14 over 55. Conditioning renormalizes the law to what you know, and chaining those conditionals gives the probability of a whole sequence of events. Next, we turn the idea around. Instead of building intersections, we assemble the total probability of an event from a partition of cases.